Hello everyone, this is Professor Roman. Welcome to the 8th video in my video lecture series, An Introduction to Discrete Mathematics. We are now ready to start Chapter 2, Logic. Some of this may be quite familiar to you if you've studied logic at all. We're just going to cover the basics. But I hope that you'll bear with me in any case, because you may find something you haven't seen before. It's undoubtedly true that anyone who hopes to be successful in mathematics, or really in any field of study, must be able to think logically. Mathematics in particular is based on our ability to create sound, logical arguments. The question is, how do we know whether an argument is logically sound? And that's when we turn to the branch of mathematics known as logic. But it is also true and probably surprising that logic has some very important practical applications. For example, to the design of what are called logic circuits. And they're used in computers, of course. And later in the chapter, we'll take a look at logic circuits. But let's begin with a few simple definitions. A statement is any sentence that has a truth value, true or false. Now, some sentences, such as go home and is it raining, don't have a truth value. Go home is a command. Is it raining is a question. So these are not statements. But I have a home or it is raining, those do have a truth value. And so they are statements. And it's important to understand that the truth value of a statement can change. Today is Monday is a statement. It's only true on Mondays. It's false on all the other days. That's fine. Statements can be divided into two types. Simple statements are statements without what are called connectives, and I'll explain that in a minute. So here are some examples of simple statements. Today is Monday. John's 4 years old. It is raining. 3 plus 4 equals 7. 1 plus 1 equals 5. False, but it's still a statement. Compound statements are made up from simple statements that are linked together with one or more of 5 basic connectives: not, and, or, if, then. Sometimes instead of writing if then, we write implies or implies that. You'll see some examples to clarify. If and only if. These 5 statements don't have any connectives, which is why they're simple statements. Here are some compound statements, and I put the connectives in boldface. It is not Monday. It is raining and the sky is cloudy. If today is a weekday, then I must not go to work. So there's 2 connectives here. Here's an if and only if, and I should have included that. Here's an if-then statement. Here's a statement with a connective and as well as implies that. Here's an if-then with an or, and you'll notice that I put parentheses here. And I'll talk about that later. There is lots of potential for ambiguity in more or less English statements. The sun is not shining if and only if tomorrow is Friday and there are no clouds in the sky. This also needs some clarification. compound statements don't have to make much sense. You'll see in a minute that what we're trying to deal with is not the English language itself, but the symbolism behind it, the logical meaning behind it. Here is the formal definition of a compound statement. It's an inductive definition, and this is a perfect situation for an inductive definition. All simple statements are compound statements. If S and T are compound statements, so are not S in parentheses, S and T, S or T, if S then T. I could have written here S implies T. S if and only if T. Everything is surrounded by parentheses to avoid ambiguity. And then there's the usual limiting clause. Now here's the point of all this. Mathematical logic tells us nothing about the truth value of a simple statement. That's a matter outside of mathematics. Today is Monday. That's not a mathematical question, or a statement rather. And it's true. You look on a calendar to see if it's true or not. But one of the goals of elementary logic is to tell us whether a compound statement is true or false based on the truth values of the simple statements from which it is constructed. Here's an example. Today is Tuesday and it is raining. Logic doesn't help us decide whether today's Tuesday or whether it's raining. But once we know the truth value of those two simple statements, logic will tell us that the statement here is true precisely when it is Tuesday and it is raining, when both of these simple statements are true. That's the meaning of the word and. That's its logical meaning. So what we need to do is give a precise logical meaning to the 5 basic connectives so that we can decide whether a given compound statement is true or false. The first step is to find a way to express compound statements written in English with math, with symbols, in a more precise way. All languages, including English, are full of ambiguity. So we need to try to remove that. So look at this statement. I am a mathematician and 2 + 2 = 5. Well, if you compare that with the previous statement, today is Tuesday and it is raining, these two statements have the same logical structure. Simple statement and simple statement. Simple statement and simple statement. So the way to remove irrelevant information, like Tuesday, raining, mathematician, none of which bears on the logical structure, we use symbolic structure. So we will replace simple statements by letters. P and Q are common letters to use for this. So P and Q has the same logical structure as the 2 previous statements, without any of the irrelevant information. Okay. From the point of view of mathematical logic, it's only the logical structure of a compound statement that's important, and not the nature of the individual statements that make it up. Once we have a compound statement written in symbolic form, once we've replaced all the simple statements by statement variables. I'm not sure I use that term in the book, but they are often called statement variables. It becomes easy to determine the truth value of that symbolic statement based on the truth value of the statement variables. So here is what we call a truth table. It lists all the possible combinations of truth values for the two statement variables, both true, true, false, false, true, false, false. And then gives us the truth value of this compound statement. And the word and has the same logical meaning as it does, let's say, common meaning. It means they both have to be true. So there's a T here when P and Q are both true. Otherwise, the compound statement is false. That is the logical meaning of the word and. One note of caution, I'm not sure if I'm bringing this up later or not, is some people will write these 4 rows in a different order, so you have to pay attention to that. You can't just read the last column. Okay. So, for the rest of this section, we're going to look at the truth tables for the 5 basic connectives. This is one of them. Okay. The connectives have symbols rather than words. We would write, well, I'll show you in this table, and they also have names. So not, the connective not is written in most of the time in one of these 2 fashions. This little, I don't know what you would call these symbols. This one's the the approximately equal to symbol. And that is called negation. And is written with an upside down V, although it's not literally a V. It's just 2 straight lines at diagonals. And that's called conjugation, or is written this way, called disjunction. If then, or implies, is written with a double arrow. That's the way I write it. That's common notation, but there are other notations. That's called a conditional. And if and only if is a double arrow, called biconditional. I don't generally like saying this, but this is a table you must memorize. And I wouldn't go too much further in this video before I had these terms clearly in my mind. It takes a little time for them to really sink in, but do the best you can right now. It's common for students to have trouble remembering conjunction and disjunction. Conjunction is and this is kind of like an A, the letter A without the little bar in the middle. I don't know if that helps any, but ultimately you just have to become comfortable with them. Here's some other issues that you face in English, and I would imagine in other languages as well, and that is different phrases can have the same logical meaning. If P then Q means the same thing as P implies Q, and that means the same thing as P only if Q. And I urge you to think about these 3 statements. Convince yourself that they have the same meaning. Okay. And here are 3 examples. Conjunction and disjunction, conditional. Conditional, by the way, is also sometimes called implication. Biconditional. They're all fairly straightforward. Negation can be a little tricky. Some students have trouble with this, in my experience, so let's go over it. Here are some statements and their negations. John is sick. John is not sick. That's pretty straightforward. Some dogs have fleas. When I ask my students in class for the negation, I will often get some dogs do not have fleas. That's not correct. It's possible for some dogs to have fleas and for some dogs to not have fleas. In fact, I'm sure that's true. The negation of a statement has the opposite truth value as the statement. Some dogs have fleas, some dogs do not have fleas. Both of those are probably true. So they can't be negations of each other. To negate some dogs have fleas, it is no dogs have fleas. Not a single dog has fleas. This is critically important that you think about this until it makes sense. All cars are blue. The negation is not no cars are blue. That would be the opposite or something. There's no logical term for it that I can think of. All cars are blue. Imagine, let's just restrict attention to, say, the cars in a parking lot. Imagine that every car in that parking lot was blue. How would you negate that? All it would take is a single car to be not blue. Some cars are not blue, or there is a car that is not blue. At least one car is not blue. There's a lot of ways to say it. 2 plus 5 equals 7. 2 plus 5 is not equal to 7. There exists an integer not divisible by 5. That's similar to the some dogs have fleas. This could have been reworded. There is a dog that has fleas. Negation is all integers are divisible by 5. Give these some thought. All men are animals. Same meaning as every man is an animal. Each man is an animal. Any man is an animal. But there's some danger here. I try my best never to use the word any when I write my books. Sometimes it slips by. But any man is an animal. I can see people misinterpreting that as there is a man that is an animal. And so I try to avoid that word. But these 4 phrases are logically equivalent. They have the same logical meaning. And their negation then can be written, not all men are animals. That's sort of a direct negation of all men are animals. You could have written here, it is not true that all men are animals. Some men are not animals. The negation of all is some, but you have to add the not here. So this is for you to think about until it makes sense. There exists a man who is not an animal. Okay, and I repeated this because of the issues that some students have. All cars are blue. Negation is not no cars are blue. That's the diametric opposite. They're all blue, none of them are blue. There's a lot of room in between. So to negate all cars are blue, it would be at least one car is not blue. Or some car is not blue, or there is a car that's not blue. The conjunction of John is sick and some dogs have fleas is the statement John is sick and some dogs have fleas. The disjunction of these two simple statements is John is sick or some dogs have fleas. To translate this statement, John is at the library or he is not at the bookstore, into symbolic form, the first step is to identify all of the simple statements within the compound statement. So we have John is at the library, we'll call that P. He is at the bookstore is Q. We don't want to include not because then this wouldn't be a simple statement. Then the symbolic form looks like this, P or not Q. For this one, if today is Monday or it is not raining, then we can go to the store. So we'll let P be today is Monday, Q, it is raining, oops, and R is we can go to the store. Then this is the symbolic form. P or not Q implies R, or if P and not Q, then R. And the parentheses are important here because if we change the parentheses, we will get a different meaning. And I'll leave you to think on that. It is not true that today is Friday or we are unhappy. So today is Friday will be P. We are happy, Q. We are unhappy. It could have been we are unhappy, but this is really not happy. So I write we are happy here. The symbolic form of this statement could be either not P or not Q. And here I didn't put the parentheses. I should, I suppose. And also here. It's not always necessary. But these are two possible interpretations of it is not true that today is Friday or we are unhappy. In English, we don't put parentheses usually to clarify. It is, you could do it this way. And that would correspond to this one. Or we could do it this way. And that will correspond to this one. So English sentences can be ambiguous. And if you were to ask 10 people what the meaning of this is, I wonder if you'd get different answers, both answers, or if it is not true that is so forceful that people would think of it as this one. I'm not sure. Let P be the statement I study, and Q, I will pass this course. Then how would you write this in English? Well, this is P implies Q and not P implies not Q. And I'm going to leave the parentheses off of this one. Okay. If I study, then I will pass this course. And, oops, if I do not study, then I will not pass this course. Okay. When a compound statement is written in symbolic form, the letters that represent the simple statements are, as I said before, called statement variables. So in this case, they're P, Q, and R, and S are the four statement variables. Okay, I think we'll leave it here for now. For the next video, we'll go on to the construction of the truth tables for the 5 basic connectives, as well as for any compound statement that you are required to analyze. So thank you for watching, and I will see you in the next video.